People occasionally express puzzlement at there being such a thing as philosophy of mathematics. Such puzzlement arises from a failure to understand that philosophy, like history, is characterized not by its subject matter, but by its style of thought, by the kind of questions it asks and the way in which it goes about trying to answer them. When this is understood, phrases beginning "the philosophy of" will cause no more surprise than ones beginning "the history of." Philosophers attempt to answer questions we are prompted to ask by a quite special kind of puzzlement. This puzzlement arises from our imperfect mastery of the concepts we employ. These questions occur to everyone, but people are often content to brush them aside with answers that will not withstand scrutiny not accorded them by those lacking in philosophical curiosity. A philosopher is afflicted by an urge to subject any proposed answer to just such scrutiny, and to arrive at an answer that will stand up to scrutiny. Because, until he does, he is conscious that he does not understand, and what he wants above all is not so much to know as to understand. The characteristic philosophical question is, why can we not affect the past, although we can affect the future? Someone without philosophical curiosity may answer impatiently, because the past has already happened, or because a previous event has either occurred or not occurred, and will experience only irritation when it's pointed out that the first answer merely repeats the problem without solving it, and the second may be countered by observing that a subsequent event either will or will not occur. The philosopher is irked by the inadequacy of these answers that first come to mind. He's driven to seek one that will satisfy him. Well, why? Because when we are faced with this question, a question that asks why we cannot do something that seems on the face of it nonsensical, and find that we cannot clearly explain what makes it nonsensical, we become aware that we do not really know what past and future are. We have no firm grasp upon the concepts of past and future. Now, these are concepts we constantly employ in the current of everyday life and everyday conversation. We recall what happened a week ago or 10 years ago. We avow what we intend to do tomorrow or speculate on what will happen 6 months from now. We use these concepts all the time. Of course we understand them. And yet, by our inability to answer the question why we cannot affect the past, we show that we have only a superficial grasp of them. We are like soldiers in a battle who know enough to be able to do what they are meant to do, but have no conception of what is happening on a larger scale. We can operate with our concepts in the situations in which we find ourselves in everyday life, in the laboratory, on the stock exchange, in the operating theatre, but in Wittgenstein's phrase, we do not command a clear view of them or attain a general understanding of them, but can grasp only how they function in particular familiar contexts. This does not hold good only of the concepts we all employ in the life of every day. It applies equally in highly technical regions. Quantum mechanics supplies a familiar example. It's commonplace to remark that it's a highly successful theory. Physicists know how to use it to predict observations and measurements, and yet frequent conferences are held to discuss its interpretation. It's well understood how the theory is to be used. It's not understood what it means, that is, what it tells us about the character of reality. Mathematics generates a number of questions causing just this kind of puzzlement, and has fascinated and perplexed philosophers from Plato onwards, for two reasons in particular. First, it's difficult to say what its subject matter is, what it's about. It's reasonably clear what physics or geology or biology investigates, but what exactly is it that mathematics investigates? A standard answer corresponding to the old-fashioned division of mathematics into arithmetic and geometry used to be that it investigated quantity and space. But this unhelpful answer will no longer suffice, since there's so much mathematics that will not fit comfortably under either head. The problem is aggravated by the second puzzling feature of mathematics, the manner in which the mathematician sets about attempting to solve his problems. He uses no telescope or microscope. He does not observe anything at all. Rather, he reasons. He carries out complex deductive inferences. The first question must be answered in a way that accords with this. Whatever it is that mathematics is about must be something that can be found out just by reasoning. Philosophy resembles mathematics in this respect. The philosopher makes no observations and requires no instruments. Insofar as these disciplines can be said to involve the making of experiments, these are thought experiments. To imagine the experiment made is quite as good as actually to make it. The two subjects thus appear to be a priori. Their results do not require us to observe how the world happens to be, but can be arrived at by thought alone. They are thus independent of how the world happens to be, but would hold good, whatever it was like. They are therefore not merely true, but necessarily true. And yet, philosophy and mathematics differ in all other respects. It's a puzzle how there can be even one subject that can be investigated a priori. That there should be two, so different from one another, appears baffling. Necessary truth and a priori knowledge are topics that engage the attention of all philosophers. It seems straightforward to understand how there can be contingent truths, things that are so but might have been different. We can get to know contingent truths only through our experience of the world by observing that they're so, or deducing from what we observe that they must be so. But how does it come about that there should also be necessary truths, truths that we can know independently of our experience of the world? How is it that if we knew all contingent truths, there would be some truths left over? This is easy enough to understand concerning trivial necessary truths, such as that there are 7 days in a week, or that every widow was once married. To recognize statements of this sort as true, we need know nothing other than the meanings of the words. More, we couldn't claim to know the meanings of the words if we failed to perceive that the statements are true. But mathematical theorems are seldom trivial in this sense. We may not need to start with any initial knowledge other than the meanings of the words if we are to come to recognize them as true, but the converse certainly doesn't appear to hold. We may surely know the meanings of the words without realizing that the theorems hold good. Mathematics presents itself as by far the most capacious repository of non-trivial necessary truths, and a knowledge of it as by far the most extensive body of a priori knowledge, and this fact alone suffices to make it of intense interest to philosophers. Admittedly, certain philosophers, of whom John Stuart Mill is the best known example, have challenged the a priori character of mathematics, claiming that mathematical theories rest upon certain highly general contingent facts recognizable by gross observation. But this challenge does not alter the situation greatly. For the most that such empiricists can argue is that the starting point of this or that mathematical theory, the axioms of the theory, is a collection of readily observable contingent facts. They cannot explain why mathematicians fail to set about gathering, by devising experiments, by closer observation or improved observational techniques, other facts of the same kind as other scientists do. Why instead they content themselves with the meager supply of contingent facts with which allegedly they begin, and proceed to draw out their consequences by means of ever-lengthening chains of deductive argument. Mathematics is still a science quite unlike any other. The only upshot of the empiricist's contention is what is sometimes called if-thenism, which restricts the necessary truths discovered by mathematicians to those expressed by statements of the form, If the axioms of the theory hold good, then such and such a theorem holds also. And this leaves the problem of necessary truth untouched. That there should be such an a priori subject as philosophy is comparatively intelligible, because the philosopher's task consists principally of disentangling our concepts. It does not aim so much at arriving at new truths as at coming to understand better those at which we've already arrived. Disentanglement sometimes plays a critical role in mathematics, as indeed it does in every subject. To attain the right definition of continuous or of dimension was a step of the highest importance. Nevertheless, hitting on the correct definition of a concept, though often an essential contribution to progress, remains a preliminary to the discovery of mathematical truths, not a means of discovering them. It is not the characteristic activity of the mathematician. To explain the existence of mathematics is a greater challenge to the philosopher than to explain that of philosophy itself. The capacity for wonder is a prerequisite for the activity of philosophizing, and anyone who retains this capacity must marvel at the vastness of the body of a priori knowledge amassed by mathematicians by pure deductive reasoning. Now, having tried to convey an impression of what the philosophy of mathematics is about, I will now tell you something of Gottlob Frege. Superficially, it might be said that he lived an uneventful life. Born in 1848, his entire professional career from 1874 to 1918 was spent teaching at the University of Jena, and he died in retirement in 1925. Although he published 3 interesting articles towards the end of his life, almost all his work was completed by 1906. But his history during his lifetime and that of his reputation up to the present are both extraordinary. While he lived, very few, among them Russell and Wittgenstein, paid any attention to his work, a state of affairs that continued until after the Second World War. Now, he's universally recognized as the grandfather, if not the founder, of analytical philosophy, and wherever that school of philosophy flourishes, his works as indispensable reading for any student of the subject. Yet he was not a professional philosopher. He was a professor of mathematics, still largely as neglected by the mathematicians as he once was by the philosophers. This neglect was in part due to his originality and in part to his having chosen to devote his life to an enterprise lying on the borderline between philosophy and mathematics. With very few exceptions, mostly in the early stages of his career, everything that he wrote was directed towards or ancillary to this enterprise. He determined to rectify a situation that greatly distressed him: the inability of either mathematicians or philosophers to explain the basis of our acceptance of mathematical theories. He wanted to show what justified our belief in these theories, with what right we assumed the theories to be correct and their theorems to be true. His attempt to do this made him the first modern philosopher of mathematics. Now, this description of the task Frege set himself to accomplish is somewhat too wide. He had the traditional view of mathematics as subdivided into arithmetic and geometry, and he believed that these two parts of mathematics demanded different accounts of the grounds for our belief in them. His general remarks about geometry were almost all for the purpose of contrasting it in this regard with arithmetic. His positive work related entirely to the latter. By arithmetic, Frege meant number theory and analysis, the theory of natural numbers and the theory of real numbers. He did not view set theory as a separate mathematical theory, but rather as a part of logic, of which he believed that he could also give a satisfactory account. And indeed, if the problem can be solved for number theory, analysis, and set theory, there should be little fear that any other branch of mathematics will give rise to further difficulties. Frege thought that the inability of mathematicians to provide a justification for our acceptance even of number theory was a scandal to the science. They could not even give an intelligible account of what the natural numbers are, and hence they could not so much as say what number theory is about, let alone explain how we know that it is true. His first step in carrying out his self-appointed task was to invent modern mathematical logic. I said earlier that Frege was the first modern philosopher of mathematics. The title might be claimed by some for Kant, but Frege differed from Kant and from all his predecessors is in his determination to treat of the mathematical theories with which he concerned himself in detail, rather than contenting himself with observations which, even if sound, had not been demonstrated to hold good for all propositions of those theories. Kant had maintained the a priori character of mathematics, but had distinguished two varieties of a priori truths, the analytic and the synthetic. Analytic truths were those guaranteed by logic alone, and were, on Kant's view, all trivial. They must be recognized immediately by anyone who understood the words in which they were expressed, and hence they could not extend our knowledge. The truths of mathematics, by contrast, were synthetic and hence substantial. The recognition of geometrical truths depended on our intuition of space, and of arithmetical truths on our intuition of time. Our mathematical knowledge was nevertheless a priori, because Kant held that we possess conceptions of space and time independently of any particular experience of them, a priori intuitions. Frege accepted Kant's notion of our a priori intuition of space, and with it his view of geometry. He thought that while non-Euclidean geometries are logically consistent and hence intelligible, we know a priori that the geometry of physical space is Euclidean. But he utterly opposed the Kantian view of arithmetic, believing that neither temporal nor spatial intuition played any essential role in our recognition of its truths. In this, he was following the footsteps of the great Czech mathematician and philosopher Bolzano, who died in the year of Frege's birth. Bolzano had initiated the process of rigorizing analysis, explicitly arguing that propositions concerning real numbers, such as the mean value theorem, ought not to be accepted in virtue of their apparent obviousness to geometrical intuition, but could, and therefore should, be proved in a purely arithmetical manner. As Bolzano had striven to expel appeals to intuition from analysis, Frege wished to expel them even from number theory. Since proof is the principal instrument for establishing mathematical truths, he considered that the process of mathematical proof must be subjected to scrutiny. Do we know that all principles of proof that we use in number theory, or that we need in order to establish the basic number theoretic propositions that we frequently take for granted, are of a purely logical character? As long as we reason without paying conscious attention to the steps we take in reasoning, we do not. We may then mistake for logical transitions ones which in fact rely upon intuition. Conversely, we may suppose an appeal to intuition to be demanded by what in fact can be accomplished by purely logical deduction. It was therefore necessary, in Frege's eyes, to attain an explicit systematization of the process of mathematical proof. This he did in his first book, the Begriffsschrift of 1879, a completely original work that did not build on the recent advances in logic by Boole and his successors, but adopted a wholly new approach. Not only had they extended the scope of logic by only a small degree beyond what Aristotle had achieved, but they had provided no more than a means of encoding any given argument that fell within the scope of their theories. Frege desired something different, a language in which mathematical theorems could be expressed and their proofs carried out in accordance with strictly formal principles of inference. It is, with hindsight, astonishing that despite an intense study of logic over many centuries, indeed millennia, it failed to register the glaring fact that logical theory was incapable of analyzing even the simplest piece of mathematical reasoning. Frege's little book completely rectified this. Using a notation quite different from, but isomorphic with, that used nowadays, or by any of his successors, parts 1 and 2 of the book presented a complete formalization of what we now call first-order logic. Part 3 explored the realm of second-order logic also, that is, the logic governing statements that generalize not only over objects, for example the natural numbers, but over properties of and relations between these objects. And here, Frege scored his first success in the war against intuition, a logical analysis of the notion of a sequence. Rather naturally, it was common to think of sequences in temporal terms, but Frege observed that the notion was of far greater generality. A sequence can be generated by any relation. The term generated by I've just used itself relies on a way of picturing sequences as proceeding in time, and I should have said something like characterized by reference to. The relation R, say R, is that which any term in the sequence has to the next. Frege defined the expression B follows A, object B follows object A in the R sequence, to mean B has every property, F, possessed by every object to which either A or an object having the property F stands in the relation R. This definition and the theorems concerning sequences that Frege proved by appeal to it were not important to him merely as samples of how one could dispense by logical means with what was often thought to rely upon intuition. It was important because the notion of a sequence is fundamental to the theory of numbers, since the natural numbers form precisely such a sequence. Given the number naught and the relation that holds between any natural number n and its successor n plus 1, the natural numbers could be defined to be those things that followed naught in the successor sequence, together with naught itself. Moreover, such a definition would render the principle of induction its most immediate consequence. The principle allows something to be proved to hold good of all natural numbers by showing that it holds of naught and of the successor of any number of which it holds, and had frequently been said to be a form of inference peculiar to number theory. But Frege's definition of natural number reduced it to pure logic. Plainly, investigation of what justifies our accepting mathematical theories other than geometry must begin with the most basic theory, number theory, and the first step might be expected to be to axiomatize it. It's odd that despite the praise conventionally lavished on Euclid for his axiomatization of geometry, no one attempted to do this for any branch of arithmetic until the 19th century. We can extract an axiomatization from Frege's work, more precisely an abstract characterization about which he proved any structure exemplifying it to be isomorphic to the natural numbers. But he did not proceed in this way. After what he had achieved in his first book, it's unsurprising that he came to believe that the whole of number theory could be derived from logic alone. In 1884 he published The Foundations of Arithmetic, in which, having subjected all existing accounts to deadly criticism, he sketched his own demonstration of the logical character of number theory without using his logical notation. In 1893 and 1903 he published the first and second volumes of his Basic Laws of Arithmetic, which set out fully formalized proofs in his logical system, both for number theory and for analysis. Given Frege's view that all arithmetical notions can be defined in logical terms and all arithmetical propositions proved from logical first principles, the task of justifying arithmetic necessarily involved for him much detailed mathematical work, of which his books are full, largely neglected, if only because very few were prepared to learn to read his symbolism. But the task involved philosophical argument also, if the mathematical proofs were to be shown to establish what was claimed, and in the process of carrying it out, Frege turned himself into a philosopher, and one of genius, as well as a mathematician. Although his philosophical work was restricted in scope, he plainly became interested in the topics he tackled for their own sake, so that his discussions, particularly in the ancillary articles that he wrote, extend well beyond what was strictly necessary for his primary objective. It's this that has made them of such vivid interest to modern philosophers not especially concerned with the philosophy of mathematics. But that's not our present concern. What, to my mind, makes him of primary importance to present-day philosophy of mathematics is the clarity with which he presented its problems, even when he did not attain more than partial solutions to them. For these are often problems which later writers have scarcely attempted to tackle. Given his conclusion that analytic truths cannot extend our knowledge, Kant could not regard mathematical truths as analytic, since, on the face of it, mathematics massively extends our knowledge. Frege, having decided that arithmetical truths are logical in character and therefore analytic, was faced with explaining how it is that analytic truths can extend our knowledge. And this is the same problem as how deductive reasoning can lead to new knowledge. For such reasoning to be valid, a single inferential step must be both recognizable and compelling. Anyone who understands the statements figuring as premises and conclusion must thereby grasp that acknowledging the former as true requires acceptance of the latter. But if this is so, how can a sequence of such steps take you any distance from where you started? The problem has been addressed by few philosophers other than Frege, notably by Mill, and none has offered a satisfactory solution. If Frege's solution is not correct in detail, I'm not going to give the detail, it must, I believe, be correct in outline. For Frege, not merely to discover a deductive argument, but even to follow it, is to engage in a creative act. That is because it involves more than merely understanding the statements involved. To understand the statement, to grasp the thought it expresses in his terminology, it's necessary to apprehend its structure, how it's put together out of its parts. A sentence is not just a string of words. But to recognize the validity of an argument in which it figures, we need to do more than this. Sentences exhibit patterns, to use a term Frege did not employ, that we do not need to discern in order merely to know what they say. It's on the relationship between these patterns that the validity of an inference depends. A pattern is not imposed, but is there to be discerned. But discerning it is an intellectual act and not mere passive reception. Frege is sometimes supposed to have thought that arithmetic describes the Platonic realm of abstract objects having no connection with contingent reality. Such a view would provide no room for the application of arithmetic, though in fact even Plato's ideas bear a direct relation to the empirical world, but the misrepresentation of Frege is nearly total. The real Frege gave a more central role to application than almost any other philosopher of mathematics. The applicability of mathematics is nowadays often described as miraculous. Frege would have denied not merely that it was a miracle, but that it was even a surprise. It is applicability alone, he wrote, that raises arithmetic from the rank of a game to that of a science. His view of application was a subtle one. Arithmetic must remain pure, any importation of notions relating to particular empirical applications would sully that purity, and he criticized both Mill and Helmholtz on this ground. But the general principle exemplified by every application of a fundamental mathematical notion, and in particular by the notions of the natural numbers and of the real numbers, must be discerned, formulated, and made central to its definition, not tagged on as an appendage, as Dedekind did in his treatise on the natural numbers. Rather, the general principle in accordance with which all applications are made must be incorporated in the definition. That's why Frege held that since the fundamental use of the natural numbers is to specify in finite cases how many objects there are that satisfy some given condition, they must be defined as cardinal numbers, not indeed of objects of any specific kind, but of objects of any kind whatever, since all objects can be counted. And it's also why Frege regarded the definitions of the real numbers given by Kant and Dedekind as unsatisfactory. Though their definitions were different, both assumed the rationals as already given, whereas on Frege's view, the term number is used in just the same sense in rational number as in real number, so that the rationals ought not to be defined separately in advance of the real numbers, but simply as a particular type of real number. By contrast, the term number has a different sense in natural number, making it necessary to define the natural numbers separately. The natural numbers serve to answer the question, how many? So they, together with the transfinite cardinals, are numbers in one sense of the word. The real numbers, including the rational ones, serve to give the ratio of a quantity, a mass, a temporal duration, an electric charge, etc., to a unit quantity of the same kind, and are therefore numbers in a different sense. They must therefore be defined as such ratios, not between quantities of any specific kind, but between any two quantities of the same kind. That, of course, requires a prior analysis of the notion of a quantity, or range of quantities. I've been describing a number of near misses. Frege's account of the fruitfulness of deductive reasoning must be close to the truth, but I don't think it was the precise truth. His emphasis on the applicability of mathematics was surely correct, but his demand on the way mathematical concepts are defined is difficult to satisfy. He was clearly right to maintain the necessity of arithmetical truth, and to deny that this had derived from intuition in Kant's sense, but from features of concepts sharing with logical ones their applicability to any domain of discourse, even if he was wrong to claim them to be strictly logical in character. The most interesting of all the components of his philosophy of arithmetic is, however, the most contentious. It attempts to resolve a problem that hardly any of his successors has faced. It's not a single thesis, but a complex of ideas that can, with difficulty, be disentangled from one another. And it's quite certainly wrong as a whole, because it led Frege into the catastrophe that caused him to acknowledge that his life's work had been a failure. Someone who knew nothing about Frege, but learned that he believed arithmetical theorems to be expressible in purely logical terms and provable from purely logical principles, would expect, on reflection, that he did not take statements of arithmetic at face value. The statement, pi is transcendental, is on the face of it of the same form as Clinton is unsuccessful, and says that a particular object of a certain kind has a specific property. While there's a prime number between 44 and 52 appears to be of the same form as there's a small country between France and Spain, and says that some object of a certain kind has a particular property and stands in a specific relation to two named objects of the same kind. But statements of forms such as these are hardly candidates for being propositions of logic, for the principles of logic must hold independently of which particular objects, or even of how many objects, there may happen to be. So it appears to follow that Frege did not think that arithmetical statements are truly of the form they appear to be. He must rather have construed them as disguised versions of statements of very different forms. For instance, reinterpreting any proposition referring to a natural number n as involving the statement that there are n things of some kind. Well, this conclusion is highly reasonable, but it is wrong. Frege did understand arithmetical statements at face value. Numbers were, in his view, objects. It followed that logic must, after all, guarantee the existence of certain abstract objects, indeed of infinitely many of them. Numbers are what he called logical objects. Now, this didn't, to any significant extent, hamper his account of the application of arithmetic. Mathematical theorems were for him encapsulated results of complex chains of deductive reasoning, enabling us, by specializing them to less general cases, to pass from contingent premises to contingent conclusions without having to carry out the reasoning process afresh. The existence of the objects constituting the elements of the structure which each particular theory, number theory or analysis, treated, was guaranteed by logic, and in this sense the purity of arithmetic was secured. But they were not pure in the sense in which set theorists nowadays speak of pure sets. A pure set in this sense is one whose transitive closure contains nothing but sets. That's to say, every element of the set is a set, and every element of an element of the set is a set, and every element of an element of an element of the set is a set, and so on. On the contrary, for Frege, natural numbers are cardinal numbers. And a cardinal number n is the class of all classes with just n members. Since that includes classes whose members are empirical objects, there's no problem how theorems about natural numbers can be applied to empirical circumstances. Likewise, real numbers were for him ratios between quantities, and such quantities include physical magnitude such as mass and length. The theory was designed to be directly applied, and the fact that the numbers with which it deals are taken to be objects in no way hinders its applicability. What is problematic is how the existence of logical objects can be justified. Logical objects form a special class of abstract objects, called by Frege non-actual objects because they don't act on other objects or bring about effects in them as physical objects do, and are therefore not perceptible by the senses. His account of what we do when we refer to non-actual objects was based on his celebrated context principle. This principle says that it's only in the context of a sentence that we can refer to anything. Otherwise expressed, we can't mention anything without saying, save as part of a process of saying something about it. Expressing a thought about it, not necessarily asserting anything about it. This principle is the most profound, the most difficult, and the most contentious ingredient in all Frege's philosophy. Philosophers who deny the existence of abstract objects are labeled nominalists. They usually characterize abstract objects precisely by their not being actual in Frege's sense, that is, by their lack of causal powers. And the standard nominalist argument against their existence is that since they cannot affect anything, everything must appear exactly the same if they do not exist as if they do, and hence that we can have no reason to suppose them to exist. Well, the equator is cited by Frege as a non-actual object. So suppose you're in an aeroplane and you remark to your neighbor that the plane has just crossed the equator. To your surprise, he doesn't know what the term equator, he doesn't know the term equator and asks you what it means. You try to explain to him and he asks whether you can see the equator or feel the equator. When you tell him that it's not that sort of thing, he asks what reason you have to suppose that there's any such object. seeing that everything would be exactly the same if they were not. You can do no more than patiently explain to him how sentences containing the term the equator are used, and in particular how we judge of their truth and falsity. And according to Frege, in order to justify the use of the term the equator, you need do no more than that. This is what is meant by saying that it's only in the context of a sentence that we can refer to an object, or at least to an abstract object. And we may add, what's intended to be part of the content of the context principle, that when we know how sentences mentioning such an object are used, we thereby know what it is to refer to that object. Well, in my view, this is a wholly satisfactory vindication of the general vindication of the use of terms referring to abstract objects, and there can therefore be no doubt that the context principle is in broad outline sound. But we should not jump to the conclusion that abstract objects present no further difficulties, and Frege did not jump to that conclusion. To justify the use of abstract terms of any given kind in the light of the context principle, we must be able to do what that principle demands, that is, to explain without circularity the use of sentences containing such terms and the conditions of their truth and falsity. And this is by no means always a simple task. Why did Frege require that numbers be recognized as objects? To use the example that pi is transcendental should be treated as being of the same form as Clinton is unsuccessful. His primary reason was to guarantee the existence of sufficiently many elements of each theory for all possible applications of it, while preserving the purity of arithmetic. It's easy to imitate Frege's constructions at a higher level. For example, take cardinal numbers as properties of objects, so that they're no longer themselves construed as objects. And that's essentially what Russell and Whitehead did in Principia Mathematica, taking properties for this purpose extensionally. The drawback of doing this is that one can't guarantee that there are infinitely many natural numbers. The solution adopted by Russell and Whitehead was to assume an axiom stating that there are infinitely many individuals, a proposition certainly not a logical truth and dubiously true at all, and thereby the entire project of deriving arithmetic from logic was abandoned. Similar difficulty arose with the real numbers. It was by taking numbers to be objects that Frege was able to circumvent this problem. He insisted on the generality of the notion of cardinal number. Objects of all kinds can be counted, and among things that can be counted are numbers themselves, as when we speak of the number of roots of an equation or of prime numbers less than or equal to a given number. So numbers must be objects, since a cardinal number is always the number of objects satisfying some given condition. And this allowed Frege to prove the existence of infinitely many natural numbers independently of the existence of objects of any other kind. We can show a number n to exist by producing a predicate true of just n objects. So the number naught exists, since is different from itself, is true of naught objects. And so is the number naught is true of just one object, and hence the number 1 exists, and is a term of the sequence naught 1 is therefore true of just two objects, and so the number 2 also exists. And in general, given the existence of the numbers from naught to n, the number n plus 1 must exist, since it's the number of terms in that sequence. This is an informal sketch of a theorem Frege proved rigorously from his assumptions. The assumptions are easily stated. Natural numbers were to be treated as cardinal numbers, and the basic notion for the theory of cardinality is that expressed in natural language by saying that there are just as many objects of one kind as of another. Frege adopted as a definition of this notion one that had recently been accepted by other mathematicians of his day, namely the existence of a relation mapping the objects of the one kind, one-to-one, onto those of the other. He tacitly assumed that every term standing for a cardinal number could be framed by means of the operator the number of objects which, so. Given that by appending any well-defined predicate to this operator one would obtain a term standing for an object, and given the definition of just as many, Frege formulated a fundamental equivalence, namely, the number of objects of one kind is the same as the number of objects of another, if and only if there are just as many objects of the one kind as of the other. This fundamental equivalence looks at first sight tautologous, but it isn't. It's a principle governing the introduction of terms standing for numbers. The right-hand side says nothing about any such objects as numbers. The left-hand side says that the numbers denoted by two basic terms for them coincide. Now, against that background, Frege proved, by means of suitable definitions, that all the basic principles of number theory could be derived by means of second-order logic from this fundamental equivalence. So a justification for the fundamental equivalence is required. If the introduction of terms for cardinal numbers is to be defended by appeal to the context principle, we need to show that we've succeeded in specifying the condition for the truth of any sentence containing such terms. And Frege discussed whether the fundamental equivalence could itself be regarded as effecting this. Well, some present-day philosophers of mathematics enthusiastically answer yes to this question, or to some rather similar question, but Frege's own answer was no. So he resorted to his definition in terms of classes. The number of objects of a given kind is the class of classes A, such that there are just as many objects of that kind as members of A. The only use he made of this definition was to derive the fundamental equivalence from it. Its purpose was simply to introduce terms for numbers in a way he considered unexceptionable. His ground for denying that the fundamental equivalence served to do what the context principle required was that it failed to determine the condition for the truth or falsity of a statement of identity between a number and an object denoted by a term, not given as a number, not formed by means of the operator, the number of objects. The objection is sound, but he overlooked a far more basic one, namely that the fundamental equivalence does not even determine the truth or falsity of every statement of identity between numbers. It doesn't, for instance, give us any means of deciding whether the number of natural numbers is or is not the same as the number of all cardinal numbers, or of all objects whatever. Now consider what Frege was about. He was trying to justify the introduction of terms for cardinal numbers satisfying the fundamental equivalence. The numbers denoted by those terms were then to be treated as belonging to the same domain of generality as all other objects, so as to be covered by the quantifiers for every object x, or there is an object x. And in accordance with this, the terms being introduced were to include ones for the number of cardinal numbers of some given kind, as specified by means of some predicate numbers. It's essential for the proof of the infinity of the natural numbers. And all this was to be done without first specifying of what objects the domain of generality was to consist. The procedure has a troubling circularity. Which objects there are depends on which numbers there are, but which numbers there are depends on which objects the domain contains. Well, what are we to say about this situation? Should we say, as the philosophers I mentioned believe, that the conditions required for appeal to the context principle were too stringent, need not determine the truth value of every statement? If so, just how could they be weakened without destroying the plausibility of the principle? Or should we say that the whole procedure is misconceived? The usual conception of how an interpretation of a formal theory should be laid down is that one should begin by specifying the intended domain over which the variables are to range, and then interpret, with reference to that, the expressions special to the theory, saying, for example, of which elements of the domain some given predicate is to be true. So, according to this conception, it's impossible simultaneously to determine the domain and the interpretation of the symbols intended to denote elements of that domain. But if that's the only way in which one can go about laying down how a mathematical theory is to be understood, we can never explain how a fundamental theory, such as we can never explain a fundamental theory, such as number theory or as analysis. By a fundamental mathematical theory, I mean one whose elements cannot be defined as resulting from some simple operation on those of another theory, and this amounts in practice to one with a greater number of elements than any prior theory. The natural numbers form the prototype of a denumerable totality, one all of whose elements can be generated as the terms of an infinite sequence. It's by grasping the conception of the totality of natural numbers that we first come by an understanding of the phrase infinitely many. Likewise, the real numbers form the prototype of a larger infinite totality, that is, a non-enumerable one with too many elements for them to be generated as the terms of a sequence. Our problem is to explain how we first attain a conception of a totality of the one or the other size, or cardinality. So long as these theories are presented to us before any others with domains of these sizes, we have no means of specifying their domains in advance of expounding the interpretation of the theory as a whole, and yet we do come to understand them. It seems that Frege must have been right in thinking that for these fundamental theories we have to acquire a conception of the domain simultaneously with that of the meanings of the basic notions defined over it, and yet such a process appears doomed to vicious circularity. It's one of the great merits of Frege's philosophy of arithmetic that it faces this difficulty squarely. Even if his attempted solution up to it failed, he addressed a problem that's usually ignored but cannot be evaded. His solution did indeed fail, catastrophically. I have discussed the point as it applies to the cardinal numbers taken as introduced by means of the fundamental equivalence, to make clear that it doesn't relate either to the consistency or to the power of the method of introduction. But Frege rejected that method and gave instead his definition in terms of classes. But that just shifted the problem to the justification for introducing classes. This he effected by a method precisely analogous to the use of the fundamental equivalence. He treated the operator, the class of objects which, as a primitive symbol, forming a term standing for an object whenever supplemented by a predicate of objects, laid down an axiom stating that the class of objects satisfying any given condition is the same as the class of those satisfying some other condition, just in case every object that satisfies either condition also satisfies the other. The only difference was that in this case he had a supplementary stipulation to handle the case he believed to give rise to the only problem, that of a statement equating a class with some object not given as a class. And notoriously, this axiom rendered his system inconsistent. It yielded the celebrated paradoxes of set theory. And after struggling to escape this calamity, Frege accepted that his entire life's work had failed. In setting out the problem, I've tacitly relied on an attitude towards mathematical objects that we naturally have, but seldom remark on. Frege took for granted that the logic appropriate to mathematical theories is that we now call classical, one that assumes every statement to be determinately either true or false, and considers the truth or falsity of a complex statement to depend only on the truth or falsity of its constituent substatements, or in the case of a universal generalization or existential statement, of its instances. This assumes that the operations of generalization or existential quantification will preserve determinateness of truth value. That is, we shall always obtain a statement determinately true or false by attaching, say, every number, or there is a number which, to a predicate definitely true or false of any specific number. Well, just consider the empirical case. What then do we require of a domain of generality if this is to be so, if that's to be enough to guarantee determinateness of truth value? We normally assume it's sufficient that the concept by means of which we specify the domain should have determinate application and determinate conditions for identity. To guarantee a definite value, true or false, for every statement about all stars or all books, and every statement to the effect that there is a star or a book of a certain kind, we take two things to suffice. That the concept star or book should have a quite precise application, no borderline cases, and that it should be definite what counts as the same star or book. We don't need, in addition, to lay down what stars or books there are. Reality does that for us. Now, this assumption may be challenged. I'm not concerned with that. I'm concerned with the contrast to how we normally think about mathematical objects. To endow every statement about all real numbers, or asserting the existence of a real number of a given kind, with a definite truth value, we don't normally think it enough to lay down what's to count as a real number. Following Dedekind, we might do that by requiring it to have a determinate relation of magnitude to every rational. But that would merely tell us how to recognize a real number when presented with one. It doesn't tell us what real numbers there are, and it would need a very robust realism about mathematics to think that that could be left to mathematical reality to determine. Normally, we think that that's something that we have, by some means or other, to circumscribe. Frege might be accused of having believed that it was how classes or cardinal numbers could in general be specified, and the conditions under which two such specifications determined the same class or number, but that would be unfair. He asserted a need to supplement any such account by certifying that it did confer on every statement of the theory a definite value, true or false. But unhappily, his attempted proof of this for the theory with classes was fallacious. And because of this, he left unresolved the problem to which he thought he had found the solution. My own view is that, as it stands, it cannot be solved. Frege sought a justification of our arithmetical theory satisfying three criteria. It must accord to arithmetic the status of a science, that is, a body of truths. It must exhibit it as apt for application to empirical reality, while not itself invoking any empirical notions, or ones derived from spatial or temporal intuition. And it must leave intact the classical theories, including the classical canons of mathematical reasoning. It's probable that no account of what justifies arithmetic can satisfy all three criteria. No means exists to circumscribe the totality of real numbers without circularity and in so definite a manner as to warrant confidence that every general statement about them has a definite truth value. It wouldn't even be any use to relinquish the requirement of the purity of arithmetic. The classical continuum cannot be derived from physical reality as we experience it, but is rather a concept generated within mathematics and imposed by us in thought upon physical reality. Rather, we should see the totality of real numbers as an irremediably indeterminate one. We can prove some statements about all real numbers on the basis of a knowledge of what must hold good of anything, for it to be a real number, and we can prove some statements that a real number of a certain kind exists by finding a way to construct one. But we do not have so sharp a conception of the totality as to justify our assuming every statement of either kind to be true or false independently of our being able to prove or refute it. And if that's right, we are not entitled to reason in accordance with the canons of classical logic. A weaker logic that we should be justified in using has long been in existence, so-called intuitionistic logic, used by constructive mathematicians. Most mathematicians are reluctant to restrict the allowable methods of mathematical proof in this way because they value the power of classical reasoning. But there's no real merit in presenting mathematical results in a form more coarse than a careful attention to the meanings that can be legitimately attached to them would warrant. It may well be that a version of analysis purified in this way would prove better adapted to what Frege prized as the basis for accounting it as science, its application to the physical world.
Thank you, Michael, very much. When I was preparing an introduction for Michael, I ran into a puzzle. I wanted to try to convey clearly, very briefly, totally non-technically, the kind of work that Michael did, and I found that a lot of the things I was noting down sounded very much like Wittgenstein. So, question, what's the difference between Michael and Wittgenstein? And Michael has, I think, himself told us, given us the slogan in his own lecture. There are, of course, myriad differences in detail, but what's significant beyond that is the very existence of the detailed, fully articulated, and carefully elaborated account. Michael has told us that what distinguished Frege from Kant was Frege's determination to work through his problems in detail. And that is indeed, as I believe this lecture has given us some sense of, what singles out Michael himself and makes him the truly great philosopher that he is. And I'm very proud to have him here for this lecture. Thank you, Michael. Now, we've had a bit of a gap. We usually try to leave a moment or two for people who aren't able to stay a little longer for a question period. But in a moment, if it's all right with you, Michael, yes, we'll have some questions, followed then by the award presentation of the award later. That was wonderful. Oh no, it was this beautiful making clear for the people who don't know about it.
Yes,
I mean, it was the, you did the balance, I thought, wonderfully.
Oh, thank you very much.
Because it's terribly, yes, it's terribly complicated, and one doesn't want to say what's not exactly right.
Sure.
Yeah,
right. Yeah.
Can I bring you this glass of water?
Yes. That's quite needed.
I wondered if at some point I should bring it over. I thought, well, that's a little distracting.
That also looks pointed.
Right. On the other hand, when I heard you coughing, I thought...
Yes, well... I'm sorry, it was a bit long.
No, we didn't. They take an hour, and you took an hour.
Yes, right.
Yes. No, we intend that's... just is that. Can we start, please? I mean, if people would be a little quieter, and I think you need all this time to get yourselves organized. Well, it's really these people who are...
That's the one.
Oh, yes. David Papineau.
Yes.
Could you elaborate on that? And in particular, I take it that you're not using this issue of getting Frege consistent.
No, it's...
As when you go to the table.
No, that's the whole point of this example. That it's certainly perfectly, it's even provably consistent. If you take the fundamental equivalent, what I call the fundamental equivalence, as an axiom, and with that definition of just as many as a one-one mapping, it's certainly in a setting of second-order logic. Frege's derivation allows you to get the whole of arithmetic by that way, and the theory is provably equivalent. It's not equivalent, I beg your pardon, consistent. So the objection is not inconsistency. The objection is what the context principle demands. The introduction of a range of abstract terms is supposed to be justified, providing that you can lay down what the truth values are to be of sentences containing that term, the truth values, or in the case that reference to the empirical world is necessary, at least the truth conditions, right? And I just remark, the problem of identity statements, which are what are directly dealt with by the fundamental equivalence, doesn't just arise for ones with numerical terms on one side and some non-numerical terms on the other, which is what Frege makes all the fuss about, but even for cases when there are numerical terms on both sides. How are we to decide? I mean, quite obviously, unless we know a lot more about what there is in the domain of what objects there are, we can't possibly decide identity statements of the kinds I cited. For example, the number of natural numbers equals the number of cardinal numbers. So there's a choice here. Either the context principle only justifies the introduction of these abstract terms if it really does settle, or show you how to settle in the case of things involving empirical matters, the truth of every statement containing one of these terms, or we've got to place much less onerous requirement on what has to be done in order to justify the introduction of abstract terms by appeal to the context principle. I don't know exactly what that ought to be or what would make it compelling. So, Frege doesn't acknowledge this fact. That's all I complained of.
Michael, can I borrow this applause?
Yes, please.
Track back to the very beginning, to put it briefly, the miracle of the applicability of mathematics to real nature. And then we have a long story about numbers, but in my domain, where one hears this, is about much different kinds of branches of mathematics, like group theory.
Yes.
Isn't it amazing that the elaborate mathematics of group theory has any bearing whatsoever on reality or Hilbert spaces?
Yes.
So I wonder if is there a connection that you can trace briefly for us to how to think about the other branches of mathematics that get used in modern physics?
Well, I'm not sure that I can, but I mean, what I gave is the recipe for. Frege says there is a question about applicability, that says some theory ought to explain how mathematics gets applied. And the only theory that can explain this is mathematics itself. Otherwise, he says, the question falls into the void, right? The philosopher, the physicist says this. not my business, and the mathematician says it's not his. In the case of group theory, I can't answer this very well. When you're introduced to the notion of groups, you're normally introduced to it via the notion of a transformation of some kind, a set of transformations closed under obvious operations, under composition and inverse. When that's not enough, the whole idea Frege has, and I said it's very difficult to apply, is you should look to see what is the most general characteristic of the theory that enables one to apply it, and then you should define the notions in those terms. That's not very easy to do. I don't even know whether it's practicable. But, well, you can say whether you think that's... Look, group theory is a very sophisticated theory, but it starts with this notion of a transformation, and that enables you to get a grip on something. So I don't know that I can say any more than that at the moment.
I've got a historical question, probably that will suffice if not, and we don't want to deeper interpret a question about Frege. What is the relationship between Frege's particular advances in the philosophy of mathematics and the work of Kant?
That was a question discussed between Frege and Peano themselves.
That is why I hope you might shed some light.
Yes. Peano derived a great... I mean, Peano was concerned somewhat... No, that would be wrong to say. But Peano was concerned to develop certain kind of foundational presentation of mathematical theories in a systematic way. But he wasn't, I think... A lot of what Peano did was actually derivative. Even what we call the Peano axioms were given by Dedekind in the first instance, that particular axiomatization of number theory. And, well, I don't know that I can say a great deal more than that. I think that the logical notions that Peano used were probably derived from, in part, from Frege's own work. I may be wrong about that. This is a historical question, as you said, and I'm not dead certain of the answer to it. The historical question wasn't what was discussed between Frege and Peano. What was discussed was questions of rigor, and Frege objected to the kind of definitions that Peano
Is it fair to say
used.
that mathematicians credit Peano with steps in the foundations of mathematics more properly according to Frege?
Probably, yes. Mathematicians, yes, almost certainly. They credit nothing to Frege. Yes, and they also, as I said, probably still credit to Peano things that were due to Dedekind. I'm not trying to detract from Peano's reputation. I'm afraid things I said just sound a bit like that, but I think, look, if you look at Russell's Principles of Mathematics, he there very openly uses a lot of work done principally by German mathematicians. He doesn't attempt to pretend that that it's all his own work, by no means. But that's a very useful summary of a lot of foundational work that existed right at the beginning of this century. I think that Peano did something of the same kind. He systematized a lot of stuff. but I think that a lot of it wasn't due to his own work. No. Do you think that's wrong?
Oh, no, I think that's right.
Uh-huh.
Let me refer to others before approaching my door.
Lorena? Can you speak more loudly, please?
I couldn't catch it.
No.
No. Yes. Well, I think he was much more on Russell's side than on Poincaré's. So far as I know, he never took any notice of the particular dispute between those two. But certainly he was in the same sort of position as Russell, namely, he did not think that induction was a form of reasoning special to mathematics. On the contrary, he made a very specific point of what Russell later, perhaps independently, made a point of. This definition that I cited allows us to exhibit, if we define the natural numbers using this definition of a sequence, then induction falls out as an immediate consequence of it, and therefore not as depending on any special mathematical principle of reasoning, but as just on purely logical principles, given this definition. Poincaré's position had to do with the idea that you have to use induction in seeing that a system is consistent, or the proofs, all proofs from the axioms are going to yield true conclusions or something, which is true in a way, but it doesn't seem to me to invalidate the position of Russell and Frege. I mean, it's like saying you can't show a logical system to be sound because, look, in your argument, you've used some of the principles of that logical system. Well, of course, any argument has to use some principles. But there's a difference between a form of argument that you use and one that is the object of your reasoning, that you're talking about. So I don't believe that argument of Poincaré's is sound. At any rate, if from the point of view of the purely historical question, Frege was certainly on Russell's side and would have been against Poincaré if he had read him. Oh yes, he said it perfectly explicitly. Well, I can't give, he certainly says it in the Foundations of Arithmetic. I can't give you an exact reference at the moment. I haven't got the book with me, but I'll send you a reference. Correct me if I don't exactly answer your question. I haven't quite got it. But the thing was, there was this long correspondence between Russell and Frege, in the course of which Russell kept trying all sorts of possible ways out, and Frege, with great confidence, despite this disaster that had occurred to him, with great confidence kept shooting them down and saying, you can't say that. And in the middle of it, Frege announces that he's found this solution, which then Russell pays no attention to and says, you're probably right. But, and actually, of course, the solution didn't work. Now, the thing about that is, it's surprising it took so long. It took Frege till 1906, I think, to recognize that it didn't work. I don't think he ever knew that you can still get a contradiction in his system. I'm not sure. But he certainly must have known, as soon as he addressed himself to the question, that the proofs he had given would break down under this weakening. It wasn't a weakening of Axiom 5. It wasn't weakened enough to avoid contradiction, but nevertheless it was weakened enough to invalidate the simplest proofs in his theory. You couldn't even prove, using that naught is not equal to 1. That's fatal for any foundations for arithmetic, obviously. And I think you can locate the exact point at which he realized that, slightly indirect, but not very indirect, namely in August 1906. And after that, he simply acknowledged that his work in the philosophy of mathematics had crashed, right? And he thought all that remained was the logic. That was all he had achieved, but not the theory of classes, not the value ranges, and therefore not the foundations of number theory or analysis. I ought just to say this, I suppose. Well, no, perhaps I'll wait and say something more in a moment. We'll see.
Frege is justly credited, among other people like you, with being analytical working foundations of mathematics and philosophy. But people often forget that at the same time there was another converted mathematician in Germany who was engaging in similar kind of enterprise, and I'm talking about Husserl. It's known that they were in fairly close correspondence for a good 20 years at least. Could you just say what you perceive as the main difference between the research programs? Because at the outset it seems that they shared a good deal of intuitions about philosophy and mathematics, but later their programs diverged dramatically.
Yes, this is a contentious matter. People disagree about this quite a lot. So I'll just say briefly what I think. It's true that Husserl was a converted... No, they're not exactly similar. Frege was not a converted mathematician. He remained a mathematician who also engaged in philosophy, who engaged in it while teaching mathematics and ordinary mathematics classes all the time at Jena. Well, Husserl really was a converted, someone who had started as a mathematician, moved into being a philosopher. However, that's not the main difference. Husserl wrote only one book. In fact, it was a book which was supposed to have a second volume and never did. His first book on the philosophy of arithmetic. It was written after Frege's book. It contained criticisms of Frege, and it was a book of which Frege later, 4 years afterwards, wrote a savage review. there had been some correspondence between them, and I think it's certainly known that, or reasonably guessed, that Husserl was deeply hurt by this review, as indeed anyone would be who read such a review of his book. I think that Frege's review was in part unfair, in places unfair. I nevertheless think it by and large fair. That is, the point at which Frege and Husserl were close was, let us say, just after Husserl had published the Prolegomena to his logical investigation, and containing this attack on psychologism. Now, I don't know whether Husserl was influenced by Frege or not, but what I do myself think is that the book on philosophy of arithmetic was a thoroughly psychologistic work. It was therefore on a basis quite different from his work at the time of the logical investigations, on the basis that he had repudiated. And I think it's far inferior work to Frege's, and didn't lead in a fruitful direction. I entirely agree that Husserl was a very interesting philosopher. I think a lot of his work is very well worth studying. I don't believe this to be true of his work on philosophy of mathematics. That's my own view. Other people think quite differently. There are some people who say the philosophy of arithmetic isn't psychologistic at all. There's very little difference between that and the logical investigations. I think this is a bizarre view. I can't... So, we'd have to discuss the text in detail, but that's my reply to it.
Michael, I think it's time to turn to more of a celebration, and I wonder if you have some closing words that you'd like you did say a moment ago we would turn back to something.
Yes, what was it I was going to say? I can't now remember.
You don't want to close by saying Frege was more interesting than Husserl.
No, I don't much want to close by saying that, but stupid. I should have said at that moment what came to me to say. I'm sorry, I'm just trying to remember what it was, because it was quite an interesting point. But, oh yes, yes, I think what I wanted to say was this. There are a lot of people who study Frege's philosophy of mathematics, but actually concentrate only on the work of number theory. And sometimes you'll see it argued that, well, maybe what he ought to have done was simply to take the numerical operator, number of objects which, as primitive, and we know that gives us a consistent theory, and that's all he needed for his construction of arithmetic and so on. That overlooks two things, or let's say it overlooks his attempt in the basic laws of arithmetic, which is very little studied and deserves study. It has some very interesting mathematical results to do a similar thing for analysis, for theory of real numbers. There's no way in which you could set about reconstructing that as it stands without using the notion of class, and you'd have to change it very radically if you wanted to base it on a consistent set theory. That suggestion simply overlooks half of what Frege wanted to do. The trouble is people read the Foundations of Arithmetic, which hardly discusses real numbers at all, and they think it's all about number theory, instead of being just as much about analysis. That's one thing I want to say. The other thing I want to say was this. You could say, Frege took the fundamental application of the natural numbers to be as cardinal numbers. Say how many things. You made this very, very plain. It's perfectly reasonable to argue that he ought to have taken their use as ordinal numbers, as when you number houses in a street, as more fundamental. Because after all, when you count a finite number of things, or even if you enumerate infinite number of things, you impose an order. It doesn't matter what the order is, particular order is, you're only interested in the cardinality, but you get at the cardinality by imposing an order. So that's one reason for saying the notion of ordinal number is more fundamental. Another reason is that without the notion of the transfinite ordinal, you have only one way of getting bigger cardinal numbers, namely the power set operation. You start with number of natural numbers, number of sets of natural numbers, number of sets of natural numbers, and so on. You haven't got the way that Kant used by considering the totality of the enumerable ordinal gives you LF1, and then there's the interesting continuum problem, how that relates to the number of real numbers and so on. So there are good reasons for saying the notion of ordinal number is more basic, actually, than the notion of cardinal number. You couldn't, this wasn't my observation originally, someone else, you couldn't set about it in the same way, or if you did, you'd run into contradiction much quicker than Frege did. Because while the fundamental equivalence which I discussed is perfectly consistent, if you tried to do that with the notion of the order type of an ordering, order type of R is equal to the order type of S, just in case there's a similarity map, an order-preserving map, the field of one to the field of the other, you just run into the Burali-Forti paradox straight away without using classes at all. So that raises a big question. How far can you push this way of introducing operators yielding abstract terms? Well, without running into inconsistency to start with. Well, I'll just leave it at that.
Thank you. So we'll close now.